Welcome, everyone. Thank you for attending. I think a few of you might have attended the first one, so I'm going to refer a little bit to the first one as we go on. So let me go ahead and start to share my presentation, and I will kick us off. Okay, can you see that, you guys?
Yeah, that looks good.
Okay. So I've chatted into the window, and so like you said, if there's any questions, you want to just say hi. We can see the questions all the time. I normally let everybody see all of the questions, and I'm sorry that it looks like that I didn't do that. If once we switch over speakers and switch over to Alan and Mike on the technical side, I will see if I can change that, because it's always nice for you guys to see each other's questions, because it tends to help generate a little bit more, make it interactive. Like we said, we'd like to have this, even though, we've got a presentation, all that sort of stuff, we'd like to keep it interactive, ask, anything you want. There's no stupid questions. I think from this group that I'm seeing here, there won't be any stupid questions at all. And some of you maybe could give this presentation, but
That's exactly what I was thinking.
maybe we'll have some guest speakers next time.
Yeah.
All right. So I'm going to go ahead and kick it off. If you guys can see that, welcome to the webinar. Today's speakers, what we're going to do a quick introduction. So if you were here last time, this will be a little bit of a repeat. I've changed things a little bit, but I wanted to give kind of a level set and introduction. And then we'll turn it over to Alan and Mike to take a deep dive into both the presentation, explanation, focusing on the AI portion of the solution. And I will refer back to, because we're not going to go over, what is HLS, how does everything work? We're going to leave that. And if you want that kind of level, I'll refer back to the original webinar, which is now available on demand, and you can get that anytime you want. So we'll look at the AI focus today. Again, I think you saw this before. We're seeing tremendous growth in the semiconductor market right now, driven by all of these AI, communication, 5G, internet, all of these things. But what we're seeing is that the traditional CPU is just not fast enough anymore. So it's really exciting time right now for all of us, because in the semiconductor industry, this has been, some of the, new IP all over the place, because we need accelerators for all of these new applications in order to get the kind of speed that we need. And there's all different kinds of, not one size fits all, right? So now even in AI, we're starting to see edge kinds of accelerators where they're looking at different power and performance trade-offs. So not everything is a one size fit all. So again, this looks to be a $1.1 trillion IC market by 2030. Really exciting growth in the market. However, we've long been trying to raise the abstraction above RTL, but RTL is really struggling. These projects are getting so big. While we've had better tools and better synthesis and better verification, we've basically fundamentally still at the register transfer level, right? So we're seeing critical time to market. I'd say most of the companies we talk to are also seeing engineering shortages. So, even if they could staff up to meet the market demand, they can't find enough experienced RTL designers and verification folks. So really struggling with that. So I think it's now is a time where we really have to focus, in this time to make the change in abstraction to increase the productivity. We just really can't stay at this level forever and ever. I did want to have a couple of things, because we've been trying to raise the abstraction for many, many years. Those of you that have been in this industry for a long time, as a few of us here have been, we've been doing it, and it has been proven. I went and grabbed some publicly available stories, and there is great value. Verification starts earlier, design is faster and easier. You can do last minute changes. You can explore architectures, which is really needed in some of the vision and AI applications. And you can bring together architecture, design, and verification much, much earlier. So again, I pulled a couple of classics from NVIDIA, which is both, cutting the whole design time in half. They had one group that is, 10x productivity from, years down to months. ST, Google with 2x faster, Facebook, who had a brand new piece of IP, who really couldn't start RTL. It really needed to explore because power and performance was critical in their AR, VR. So lots of different great success stories for raising the abstraction. However, there has been challenges, right? It's not everybody that's doing this. It's basically not broadly adopted because there has been challenges, and these are some of the ones that we've seen. Is we've seen that, moving from an HDL language, from RTL system Verilogs, um, all of that, to C-based language or raising abstraction, that can sometimes be challenging because you've got your language and your environment that you're used to. So how do I code at a higher level of abstraction? How do I code in a different language? It can be a challenge and a risk. We've also seen some unpredictability in the time. You know how long it's going to take you to code that RTL, but you don't necessarily know the right language constructs, everything to use to get that Q of R, because as you're doing the design, meeting your performance, meeting your power, meeting your area is critical. And if you can't do that the same as you could with hand-coded RTL, then there's no sense in raising the abstraction. That's like a minimum viable thing that you have to have. So it is a risk for teams that are familiar with that language. So how do you mitigate that risk? And then we've also seen that the verification has been a challenge, right? Often it's not prioritized as a first class citizen, and it has to be, so that when the verification team comes along, they need to be part of the story in the very beginning, because verification has to start earlier and be easier, right? So it can't be a challenge at the end. So these are some of the challenges that we've seen so far. So when we focused on Rise, we wanted to say, look, we really need to be able to address all of these challenges to get this broad adoption at scale. And then the other thing I wanted to point out is that as we look at creating, a raise and abstraction, one of the things we've seen is that people want to be able to bridge the gap between systems and silicon. And so the value has to be for all members of the team. You can't just have a value for the verification guys or value for the system architects and not have a value for the RTL designers. So one of the things that we've focused in bridging the gap from system to silicon is making sure that there's value for every team. So the system architects, they can get a high level model that is proven to be basically, you can look at timing and latency and enable performance analysis, especially in some of these high-end applications for AI, video, AI, to be able to do early and accurate performance analysis and identify system bottlenecks is important. So we can enable that. And then that model for the RTL designer, he can reuse that model and add architectural detail to make sure he can meet his PPA goals. So that's really important to be able to have that communication between the two using a common model and a golden a reference and a part of a system of truth, right? And then the verification earlier can start much earlier using auto-generated. So this is some of the things we'll talk a little bit more about: auto-generated transactors, plug and play, and remaining in system Verilog, because we have seen that it's just, the folks in verification land want to stay in system Verilog. And the software engineer, that's been one of the great values of raising abstraction, is because the system runs fast enough that they can then begin to develop their software early on accurate models of the hardware way before it's ready. And so one of the things we've done in Rise is that we've added system Verilog. So we support System C, C++, and System Verilog. And again, Mike showed a lot of details in the last one. I'll talk just at a very high level so we can get on to the AI stuff. But this has been one thing where we have this unified environment where you can choose the language and the level of abstraction that fits your piece of IP and fits the task that you're doing, that you're most comfortable in, and you can mix and match that. And then so what we've seen is that enables you to be able to bring all of these groups together and choose the language and the level of abstraction that fits what you are doing and what you're comfortable with. And then verification, we've seen most verification folks have already raised abstraction. They're already dealing in transactions. They're already dealing in all of the different sequences. We want to be able to keep that and pass that information and be able to have these higher level models inside representing your hardware also, because it just makes it run so much faster. This is what we do. So I wanted to say, here's what we do. We accelerate the process. We don't want to accelerate the architecture. We're just going to accelerate the hardware design process, hardware verification by using System Verilog, C++, and System C. The user develops his code at the high level, right, and provides guidance, goals, and constraints, and a technology library, because this is technology, it's a synthesis process. And I will introduce a little bit of what I mean by loosely timed and untimed. More details were from Mike in the last one. We will then synthesize that model. So we'll add implementation detail, right? Parallelism, finding the architecture, memory referencing, resource sharing, control functions, all of those things. We'll add all of that, and the tool delivers high quality RTL that's readable and can go into all of your downstream tools. So basically, this is your user code is at the high level in a high level language. And if you want to see examples of those, again, we have many examples of comparing and looking at both System Verilog and C++. But System Verilog, either untimed or loosely timed, C++ and untimed, and System C and loosely timed. And it results is RTL and the plug and play transactors for verification. So that's what we do. That is what the tool does. And one of the things that we've done that's really unique is it's really a unique solution that we're finding that we are 10 to 100 times faster for synthesis, which enables exploration, right? So we get the predictable RTL with Q of R, but a much, much faster. So that fast turnaround can enable you to try many, many different things and many different options that you just don't have time to do in RTL. The verification, we've seen that's a pretty big range, the 30x to 1000x. That's really caused by, are your models loosely timed? Do you have a little bit of RTL level in there, or are they all untimed? And if you try System Verilog and pure untimed, it's very, very fast, right? You've removed all, you can still use your favorite simulator. We're not giving you a simulation. You can either use C++, which is just compiled, and System C, which is just compiled, or use your favorite System Verilog simulator. And it will be much faster because we removed all those events from the simulation engine. So that's really it plugs and play into your existing test bench. That way the verification folks can keep the test bench, write that once, and reuse it for different levels of abstraction. Modern, integrated into VS Code. I won't go into a whole lot of that because you're going to see a lot of that when Alan kicks into the demonstration. And open and modern and built on a brand new modern foundation, which we really needed so that you have full visibility into the transformation from the high level all the way down to the RTL. So you can look at anything in the RTL and go back to see where it is in the original source code and have all that debuggability and all that visibility. And it's very modern in that we can plug in other languages. Right now, we have 3 languages, but we can also add in other things into the system. So we have an open IR inside of the tools, which is accessible and open. So things that you can plug back in. One last little explanation, and if you want a lot more detail on this, we support mixed language, as I said, and it's a pretty broad range for simulation speeds, and that's really just due to kind of how simulation works with all of the events and things that it has to manage. So the fastest, of course, is just pure untimed C++, because you're basically using the compiler, the native compilers, and you're executing your functionality on the local system. And so that's the fastest at probably 1000x or maybe even more for RTL. Next, we kind of look at untimed System Verilog, and that really brings in, and we can do this also in C++, threaded. So in order to be able, rather than having everything execute in serial, you can have things execute in parallel, basically closer to mimicking the behavior of the hardware. So we have threaded C++ solution, and then, obviously System Verilog is natively threaded through the simulator. So that can still be untimed. And then we go down to loosely timed, around 30x, maybe Mike can make some more comments of that, either in System Verilog or in System C. And that's really so that you can model performance, that you can model latency, you can model all those kinds of things where you have feedback, all those different kinds of things that you may need to model in order to do probably more control-oriented designs, et cetera. and then down at RTL. And then all of this, it's easy to mix and match within the RISE environment. So you can mix and match at the block levels. And so we automatically do all of the generation of the test bench. Now we'll do a lot more in our next seminar when we talk specifics about the verification stuff. I'm just kind of giving a bit of highlight, and our next webinar will be, nitty gritty detail on verification. But we do automatically generate all of these basically transactors and adapters to everything during the synthesis process so that you can use all of those in your verification environment. Okay. And again, we support standard libraries that are out there that have been in the open source, AC data types, AC math, FastFloat, MatchLib coming from NVIDIA. And these work in both a C++ and in a system Verilog environment to jumpstart with your IP. So you don't have to start from scratch in this. There's quite a big silicon proven library within the open source community. Okay, I will stop there. Today, we're going to have Mike talk just a little bit, who is our chief scientist, been doing high-level synthesis for a couple of decades. And then we're going to have Alan Kling, who is also co-founder of RDA, do a majority of the AI. He's been specializing in the AI solution and frameworks. And so I will let you two kick it off.
Super. Let
Thanks,
me,
Ellie.
Thank you.
thanks for joining, everyone. Let's see. Do you see
Okay,
a slide?
so
Yeah.
yes, I'm going to just talk 2 slides and just kind of set the stage for why we're even talking about AI. So next slide, Alan.
Yeah.
So if you're interested in learning about high-level synthesis, we covered this in our last webinar, and so I'm not going to go into detail, just to kind of repeat about, okay, what does it to do and why do we care? So it converts system Verilog, C++, or system C, either untimed or loosely timed, into RTL. And the beauty there is there's no misinterpretation of the spec. It generally is going to build what you describe in the high-level language into functional RTL. It does automatic pipeline insertion, so you get essentially technology independent source, and you just are synthesizing based on a set of constraints and clock frequencies. Data flow control is built in, so designing using streaming interfaces allows you again to focus on functionality, and you're not worrying about trying to synchronize different data flows within the design. You get to design exploration. So you get to explore parallelism by doing things such as loop unrolling, as well as also just being able to code at a high level lets you do a lot of architectural exploration. And then it does things like inferring memories or registers from arrays in the design. And the beauty here is you start to have complex memory architectures that, again, this is an automatic optimization that gets it right every time, and you focus on the functionality, and the tool takes care of the low-level details. So there's lots of other things that HLS does, but these are some of the big bullet points that makes it very easy to build hardware quickly of high quality. Next slide, please. So this is really why we're talking, or one of the reasons why we're talking about AI and EDA, is that there are challenges adopting an HLS design methodology. So, how do you adopt this new methodology and integrate it into existing design and verification flows without being super disruptive? And that's the problem, is that new methodologies tend to be disruptive. And as we know, that your day job doesn't stop if you're starting to investigate new methodologies, and there's a pain involved there. Part of that pain is the learning curve. So this is a different design methodology using languages that are not RTL. So it's either untimed C++, System C, or System Verilog, and they are different than designing in Verilog or VHDL. And so that is also, difficult. one of the things we've seen in terms of this adopting a methodology and part of the learning curve is having an in-house expert is always the recipe for success. So a lot of the companies that have been super successful with adopting HLS have someone in-house that's able to answer these questions about how do I do this and why isn't my design working the way I expected, or why am I not able to get the synthesis results that I expect this. Part of this is just coding for HLS. So there are rules and styles that need to be adhered to when you are coding for HLS using any of these languages. The rules are pretty much the same. And so you have to learn this. And as Ellie mentioned, I spent decades in HLS prior to joining Rise. And teaching methodology is great, but it's hard for, like I said, if you're doing your day job, to really dig in and remember what are all the rules. Along with that, you have to debug and validate this machine generated RTL. And that can be challenging because it is machine generated. And how do you verify an untimed C++ design that's been translated in RTL or System C or System Verilog? And then along with this, then it's all about optimizing your design using tool constraints. And so just running the tool, how do you know what switches to throw? How do you interpret results? Things like that. These are all the challenges that everyone faces. And so being able to have answers to these questions is key to being successful using HLS. And with that, I'm going to let Alan show you what our approach is to solving some of these challenges.
Awesome. Thanks, Mike. Thank you, Mike. Let's take a look at the generative AI aspects of what we do in Rise. If we zoom out of everything, the full technology stack we have, it is enabled, and it is due to the efficient architecture we created. We wanted to create from day one an architecture that can scale. Scale for visibility, for debug, and for efficiency throughout the entire chain. From the very top level, where we have the VS Code integration for helping us to create code, write code, analyze the design, look at schematic, looks at the quality of results. From the Python integration we have, where we can do very advanced scripting and automation, to the command line interface, and also to the advisor, which is the language-based generative AI machinery we've created. That is truly that expert guidance that Mike talked about, that we are enabling through a rack-based database using generative AI. On top of, to make the generative AI work, we are building on top of a modular infrastructure that is connected with the intermediate representations that will enable us to go from any high-level language into RTL. And we do that with a robust infrastructure for the language constructs, for all the optimizations that we covered in the first seminar on how to create highly efficient RTL from high-level design. The intermediate representation is modular, and it's hierarchical, such that it can handle any design combinations you might think of, and it's also language agnostic. And it means that we can mix and match languages together. You could have a part of the design or part of a function in the design in one language, transform that to an intermediate representation, and that in turn can be turned into RTL using a highly efficient tool chain that we use for Google, that is handling the last part of the step in the sequence, which is the technology mapping into RTL using a technology library. We also enable, for each of the transformations we are doing, we also enable verification tracing. So we know abstraction transformations, we know where data came from, what happens with it, and we use that for debug and visibility, which we also briefly outlined in the first seminar. For this is quite a stack, and because of this is quite a stack, we have separated the seminars up in different sections and spend quality time explaining how it works. For this seminar, we are focusing, of course, on the generative AI. The generative AI for us is really in the functionality that we call RISE.ai Advisor. This is the first high-level design assistant in the industry. It helps you create better code, it learn at the same time and create very efficient code. It's similar to what you're used to in any other ChatGPT or Claude or whatever you're using on a daily basis for your normal automation. It really is simply specialized to understand high-level design as a true expert. And high-level design here means that it's something you can chat with. It can perform common tasks, such as fill in a piece of code, help me understand how certain things works. We like to think about it as it helps you accelerate the code quality. So you can ask questions like, how might I go and do this? How might I go and handle some of the questions that Mike outlined as a typical challenge set for people that are starting with high-level design. But it could also be, please fill in this piece of text as I'm typing it. You're probably used to this in other normal editors where you have a language, or even as you're writing a mail, the predictions are there. We typically call that code completion or ghost texting. It's enabling that. You could also use it to build functions, build this function, this algorithm that is described. If it is known by the internet, most chat models will handle it and expand it. And again, what is unique with us is it knows everything about high-level design with RISE design automations. That means you can use it for refactoring channel interface. It can refactor code types. So in the old days, we were so used to doing a lot of refactoring in our editors, and it's very error prone. Now we can simply just use the advisor toolchain assisted by language models to do the transformation. Since the RISE advisor knows everything about RISE design tools and knows about languages, it knows about many things, it can also be used to call tools based on what the answer, it cannot answer itself. So imagine that you're asking the advisor, how fast can I run my design in a 7-nanometer technology? This is not known by the RAG model or the language model, so that has to be looked up. And that functionality is called tool use, function calling, and that is enabled in the RISE toolchain such that if the language model cannot answer what the question might be, it will start to search for tools that they can call and then in return give you an answer. And we use that extensively to help ourselves and you to create better code, get better answer, and do it in a way that is much more efficient. Here's an example on just a simple prompt that we simply will ask the language model to optimize my specific code, use these constructs, but don't do this, and it will help us understand what it is. I will show you this in a moment on how it all works. The reason why all of this is working is because, again, due to the architecture we created. We created an infrastructure based on everything we have heard from partners over our experience on how to build these AI models. And it simply goes where if you are asking a question, it goes into the advisor machinery. The advisor machinery is simply divided into sections. And the reason why it all works is simply due to the knowledge base, which is our knowledge on everything coding standard, everything data type, everything transformations of data, languages, best practices for design, best practices for verification, design structures, design patterns, and everything on implications of quality of result, such as if you write the code this way, you will get this kind of result in general. All our documentation is there, how to use the tool, how to use the Python classes, the utilities, how to run things in parallel, in serial, how to stitch it all together. Once you ask a question, it will be sent into the integrator that will try to figure out what is it you're trying to do. And this understands natural language. So just like we're used to, you ask your question in your whatever language, It speaks Danish, Swedish, German, English. You can ask it anything. It will normalize everything to its own structures, floating point numbers. And then you will basically get it to figure out if this is a request to generate something or to complete something. It will then go and send a query to the right language model that we have set up. And set up language models are very, very important because there are different companies has very different rules and wishes on what they can and cannot do and what they trust for the different language models. You might choose a language model. We have predefined them to language models that are extremely good at system-verilog, extremely good at C++, extremely good at function calling. But you could override that if you have concerns about these language models, maybe for IP rights or where they came from and who trained them, etc. That's between you and your corporations, and we can certainly set the advisor up to handle that scenario. Where the language model lives is also important. The language model can live on-premise. In this example, I will be using a consumer-grade GPU on my machine, but it could be anywhere. You could have professional high-grade GPUs, but can host massive models. We are, though, finding that the need for massive models is helpful when you have very complex prompts, then that's helpful, but they consume a lot of memory that doesn't fit into consumer-grade GPUs. So if you want to have a majority of your questions being extremely complex, then you might need to have a cloud-based solution. And we support both Amazon and Microsoft cloud-based solutions and for the advisor. But you can do any combination of mixing and matching, so to speak, for your deployment of the advisor. Wherever the language model lives, it will be categorized into what the task in hand. And as I said, if it cannot answer it with what has been trained on, what is available in the database, it will call the RISE tool chain with tool use and reason about, okay, call the tool, get the answers it needs and get it back. So from the user perspective, you wouldn't know or you wouldn't see that will go through this sequence and send the answer back. The reason why you typically don't see it is simply because the RISE tool chain is so fast, so it looks like it's just a normal prompt. But let me show you that in just a second. This infrastructure scales so well that we can build on top of the advisor to do exploration. We all know that the earlier you're doing changes in the design, the more efficient and more freedom do you have to change. So if you are changing the design at the high level design phase and set it up correctly, you can optimize for power, area, performance, throughput, whatever your KPIs are early on, and you'll get much more impact. Traditionally, in traditional HLS tools or high-level synthesis tools, this was done by brute force sweeping, where you simply take the input parameters you might have and you're observing the output and you sweep through all the combinations. And that can be a very tedious process. And it still requires a tremendous amount of data manipulation afterwards to figure out in this sea of numbers, what is it really I would like to go and see. We have a very different approach to this, and a little bit more efficient, you might say. We are using a technique called intelligent search. So instead of sweeping for configurations, we are simply just telling the language model what we are seeking, such as we are seeking the design implementation at RTL that has these parameters, these goals of area, these goals of power, these goals of throughput, and the language model will then select the sampling of the parameters dynamically such that the time it takes to search is very efficient. I will show you that in a moment. This brings up a whole new paradigm when it comes to searching for a high-level implementation that is accurate for place and route, for example, accurate for RTL. So these typical late surprises that the design doesn't fit or cannot be placed or cannot be routed, or we don't trust the RTL that it creates, the numbers and the estimators that it creates, they're totally disappearing because we are truly measuring at the end of the implementation and connecting to the place and route tool chain or synthesis tool chain, such as from DSO.ai or other tools that are very good at optimizing the tool chain themselves. We are optimizing our tool chain. What I would like to go and do is to show you the aspects of how to use the advisor to get advice for somebody like me that is a verification guy to go and create designs with advice that exists in the advisor toolchain, and then go and build exploration and search from that. So let me bring up VS Code. So here's VS Code, totally uneventful. We have a piece of RTL that is just some code. And I would like to use the interface we have with our predefined prompts. These predefined prompts are just categories of prompts that we are asking and have defined. You can create your own, you can extend it. They're context aware of the code, what you're selecting, and it will reason, going back to this diagram. It will reason based on what you're selecting. It will pick and predict and select the right language model and go back, again, based on what you're doing. So in this example, I'm simply just asking, what is really RISE's high-level design methodology? Here's the sequence of events you're following. You do the algorithm. You figure out the streaming interfaces. You have data movement. You try to optimize the design with the right directions. You go through iterations. You try to synthesize the design. Okay, that's nice. But in this example, for my design, how on earth would I do that? And again, it's context aware. So it will know for our example, not a PDF lookup. For our example, it will understand that there's a tab. It will understand that there's some data types. It tells us that we should probably go and make sure the algorithm is synthesizable. It looks like a piece of RTL. Its input is combinatorial with some clock and reset, direct input. And it has a for loop that is doing a multiply and an accumulation. What we could go and do is to ask it to say, well, how would I do this? How would I turn it into a streaming interface? It will then, again, have a predefined prompt with how do I add a streaming interface to my design. And it will say, here's what you need to do for system Verilog, for system C, for C++, system C. And here's how it might look like if you want to use it. Okay, that's helpful, but I actually want it on my design. I select the whole design so the context is there, and it will then give me a different answer because I'm now selected my entire design. I can truly just take this design, paste it in, and now I have a piece of code with my channels types. Everything is being correct. Everything is added, which is fantastic. I could probably go and ask it questions like, how would I add streaming types, streaming interfaces, fixed bit types, and it will do the same thing. Help us understand what should we do in our example for System Verilog or for C++. But let's try to run it. So in this example, we have a predefined prompt, and this prompt is generic. So it will take a look at the design code and figure out what clock to run, and it will then build the technology. Remember when we start to have terminals and we were copying and pasting, and it will synthesize the design? That it will do it, and it will do it rather fast, and it will give us an update on what is the performance we're hitting, what is the amount of flip-flops, and so forth. And that's certainly helpful. It gives an indication of what to do. But I find, and we find, when you're working with the tool interactively, this becomes suboptimal. What I'd rather do is to use the tool, right? Tool use, analyze my design, and I would like to use a certain technology and a clock. It will then go call the language models, figuring out that it don't know what the clock frequency might be and the area might be, call the RISE toolchain, send an answer back, and it will then say, well, here's what you have. You have 2 pi live stages, your clock frequency is so, your area is so. We have not enabled power simulation. It will have a log file extending to what we already have. It will have my piece of RTL that got created. All my multipliers is there. I have everything I needed in here. The RTL implementation of my design. And now I can start to figure out how can I optimize it, for example, for performance. So I could say, please optimize it for performance. It will say to optimize, you really should to apply unrolling. So this is where instead of going through the same operands or functionality, we are splitting the operands out and make it fully unrolled. And as we fully unroll it, we will get maximum performance, but we will also get the maximum design. I happen to know that we fully unroll everything all the time, so people get the fastest design, which is great, but it comes for the cost of area. So if I run the same prompt, similar prompt where we ask it just to fit it into one pipeline state, I get an area of just 5,000. And these are just a unit. It's not sizable. It's just units. And these units, I can then start to compare. So if I want to have a smaller design, I could go and ask the machine, well, how do I optimize for area? It will say, well, you should think about using bit accurate types. You should have bounded loops. Consider loop unrolling. Okay. But how about my design here specifically? What should I do here? If the answer is that I would like to have loop unrolling, I could unroll the loop. I could do it fully. I could do it partial. Partial sounds good. So instead of having all my operands being unrolled, I can just copy and paste, put it in, save it, synthesize, and now I expect a design that is significantly smaller because I do not replicate the design as many times as before. You see my area is now smaller than before. So we go through this sequence to optimize the design. We could also try to add the bit accurate types. Tell us what they are, the fractions, the total bits. We could also select the code and ask the machinery to just update my design with the code. These are predefined prompts. And again, you will find as you use the tool that there's a lot of magic in having the right prompts, and you will tune them for your exact purpose. But this is a direct translation of my design using the AC fixed data type in System Verilog. System Verilog do not allow operand overloading. So the way we handle that to use correct math functions for fixed types is we handle that with macros, and then the infrastructure will make sure that the right macros is being applied. Extremely efficient logic is created through this process, and as a result, you will get a much better design. And with honestly a few clicks and a little bit of understanding and reading what the recommendations might be. We can use a similar approach to use this to generate more. We could use it to generate test-bench structures, such as a prompt that will examine the code, be an expert. We are priming the language models. This is what we would like you to do. Instantiate the design, have the FIFO channels. Look at this, it's creating sample use cases. It knows what the functionality is, and it's creating expected numbers that I can then start to simulate in my simulator. For those of us that like maybe a less simple test structure and more something we can build on, we can also ask it to build plumbing for UVM. And it will create all the transactors, sequence items, the drivers, the monitors, the scoreboard, all the plumbing that those of us that are done this for a living would know that this takes time to build, even though you can automate some of this. This is specifically for this example, which I find helpful. We can use a similar approach to document it. And the documenter will then go and extract all the information that we have available, because it really is, everything is open, everything is text, everything is JSON. So we can extract and build reports that we can use for our own documentation. We use this functionality a lot to build test cases. So I could generate a module by a prompt, generate this module with this profile. I want this task, I want this interface, and it will build complete designs based on the functionality you're seeking. In this case, we also ask it to build a test bench infrastructure. And so it goes copy and paste, run, and execute. Once all of this is done, we can, of course, also start the GUI itself, what we call the analyzer, to take a look at the tables of synthesis report, as we outlined in great depth in the first seminar: critical path, create schematics, different kinds of schematic, all integrated into the VS Code environment. But enough about this. I'd like to wrap this up and explore how might we go and set up this design to find out the perfect implementation, not just one, but the perfect implementation for our design. So let's take a look. We have the exact same design as before. It's a Mac, channel interfaces, we read and write. In this case, we are using a trick where we have defines as the unloop factor, so we can externally control how many times we will instantiate the design. And once this is in place, we can exercise it with a test bench that is relatively uneventful. I actually created this from the advisor itself. Instantiated, have the monitor in this case I asked for, so I can measure the throughput. And then my drivers and transactors being put in, and then I dump a waveform file. I could also create a UVM structure, which I also use the advisor to create all the plumbing needed for sequencing, and both of them are executable and valid. But the exercising task in hand here is, we like to take this example, set the unroll factor, and see what is really the sweet spot for this implementation for my technology in order to meet a specific goal. To do so, I have abstracted our tool chain, which is called the builder, that handles all the communication and execution of the synthesis and validation process. The builder will then go and set defines on an unroll factor from a sequence from 0 to 32 in a step of 4. And this is just shell scripting. There's nothing magic in that. The builder itself is wrapped into another script that is using an incremental approach to build a command line. I find that helpful. You might have a different approach, but I find that helpful when I have lots of command line documents and I want to document what they do. It's easier for me to flip it up into sections, divide it up, and have parameters. Just a way to build a command line tool. Define the design, clock frequency, what should happen. We are enabling implementation. We are running, starting VCS in the background, do power, etc., etc. So while we were talking, I actually just ran all the different sequencing. So I have 8 numbers of different, 12 numbers of different designs that we have permutated with the different factors. These factors each of them has different results, different area based on how many times we have to design, different power number, etc. This table is, of course, helpful for understanding what's happening, but what is better for many of us is to see that in a little bit structured flow. Just like before, we can open the GUI, take a look at the tables that got created. we can take a look at the result itself. So this is each of the different variations of the design, the defined factors, and therefore it has an implication. For the sake of this, I like to just show that this is unfold factor 0 up to 32, and I can see how each of the different, in this case, flip-flop counts changes over time. So for example, if I was very interested in power, I could just go and say, well, I would love to see my power numbers as a function of area. I would like to see number of pipeline stages if I'm concerned about the overall throughput, or I would like to see my RTL area as a function of power. And then as a designer, I can select which of these profile or metric for my design is really most helpful for me, and I select the right ones. This is a very traditional way of doing sweeping. In this case, we have 2 parameters and 1 parameters. We locked everything down. But let's take a look at how we can do this a little bit cleverly or smarter by simply using a very simple scripting exercise. So in Vision, if you know Python, this will be straightforward. If you don't, it might need a little bit of getting used to. We just have a function. We set up the builder flow, and the builder flow will then have an instantiation of a class that is called advanced architectural study, which is extending our study. Study is the terminology we use to build designs like this set. We're intelligently searching for the design setup. In this case, we are not sweeping, we are searching, and we are finding by searching. We're setting up what is our goals. We're setting up our keys. These are the keys that we use for indexing in our database on what might be the numbers we are interested in. We are interested in the output of high-level synthesis. Our objective is to minimize it, but we will not accept more than 4,000 as the goal. Same with area, same with pipeline step. We have our unroll factor here. I added sweeping on the clock, so not sweeping variations of the clock. I'm varying the unroll factor and the clock period in some steps, and I'm varying the clocks in some steps. And in this case, I can control how many runs would I like to do in parallel to search for the optimal Pareto front. Pareto front is where at a point where we see things are only getting worse if we start to go beyond this number in a variable. It simply is now you have found a solution that is fitting that set, and you should not search longer, which is extremely helpful for finding a design. The concurrency means as we go and search, how many jobs do we have in flight before the language model is selecting the next set of solutions it go and search for. That number can be very large, but we are finding smaller numbers makes it more iterative, and and therefore finding a solutions faster, because the language model needs to know what have happened with the 2 or n numbers in flight before it selects the next sample set. So in this case, I just set it up to search for this goal, and we can simply run it. What it will do, it will now run in batch of 2, 32 times in total, and it will create a web page, which we can either look up in our normal browser, or which I like to do is just to have it in a simple browser in my VS Code. And now I'm in VS Code, and I can put it aside, I can put it outside, I can do what we are used to in VS Code, and it will give me the study that is in flight. I forgot to save the file. We'll run the study, the architectural study. I will see it here. And it's now completed. The architectural study ran in 5 seconds. It will run 42 trials. So synthesize the design with the RISE high-level synthesis toolchain 32 times, and it will search for the perfect match of configurations of the unroll factor and the clock period that fits what our objectives are, so these goals. And if we have found, 5 solutions that will fit this set, and we can then pick one or add more constraints as we zoom in. The result will be in the study itself. And once we have the study, we can see the Polaro front. We can see which solutions are the best for us to go and search for or refine further. We can see which solution was tested, what's failed. Some of them fails, right? If you cannot schedule for constraints, they will fail. Some of them will be best trials. And we can see how the sample points has a relationship to different trials. So we can see what will give us an understanding on, are we fair in our distribution or intelligent search? We can see how the language model was searching for the right combination of switches to get us to the goal of clock. And we can see how the distribution of the sample points is grouping the behavior of designs into certain categories. Extremely helpful for analyzing. Most of us will probably simply look at the Polaro front and say, this is the solutions I should go and run with. But what do you do when you really want to have more insight? Say that we really would like to have more numbers such as power and latency. You simply define a new goal where we add it, and we add a flag. So this is how the builder environment is working. We're now enabling verification, which in this case will start VCS. I just instantiate a different class, go back to my shell, and rerun. It will now run the configuration study, which has different goals. And if I go to my browser, I will now have a configuration study. This name, under 1, I add under 1. And now I can look at the Polaro front as it starts to run. It will run in batches of 2, so it will take some time for this to go through VCS. But the whole idea is, instead of doing random sweeping with lots of parameters, we use this as a vehicle to go and search for the perfect solution. Let it run a little bit. We can do the exact same thing for RTL studies. You see now it's start to pops up. We have Polaro fronts that is searching for certain solutions for our latency and power. So in less than a minute, I found there's 2 solutions that is fitting into our objective, where we are synthesizing, validating with verification, and we are computing the number of cycles, and we have power indications that is within our goals. You can easily see that this becomes immensely powerful when you start to have optimizations that is searching not so much for the high-level output, but more of the synthesis where we enable implementation tool chains. This takes a little bit of a time to run, but just for the sake of it, I'd like to show how it's done. We add new objectives. We focus on the synthesis output, not the high-level output, but the only 2 knobs we have to manipulate with is the synthesis, so the high-level synthesis input, and then we are measuring and searching for the Polaro front after synthesis. This can work, same techniques for place and route, and you can, only imagination can see how this can be applied to your environment. So in short, many different ways of using the awareness of how to run the design tools, how to do verification, how to search for perfect solutions as we go and explore how to build a design that is fitting the design objective. And with that, I would like to bring it back to the wrap up.
Thank you very much, Alan. That was great.
Thank you.
Okay.
And then I stop.
All right. Thank you, Alan.
Thank you.
Let's go ahead and do our quick conclusion. All right. Can you see my screen okay?
Yeah.
Okay, so again, thank you everybody for coming. Just quick summary. If you haven't seen the seminar, again, Alan said we're doing this in a series. So the first one really spent more time doing an introduction into everything, the tools, explaining HLS a little bit more, but really focusing on we are delivering a true mixed language environment, mixed abstraction. So you can use the level of abstraction, use the language that best fits what you're doing. And as today we've seen, we have a very unique solution that uses generative AI, and you saw both examples of using it as an expert and an advisor in the tool, and an expert and an advisor as you begin looking at design space exploration. And both of these things to dramatically affect how easily you can adopt and get better quality designs. And then lastly, which is something you'll see in the coming ones, you saw little bits and pieces of it here today, we enable verification as a first-class citizen that's built in everything that we do. You can see it was built into the generative AI solution. In the last webinar, you'll see from Mike about what the synthesis generates. And then you're going to see in the next one, the next topic that we're going to take on is really a deeper dive into high-level verification and everything we've got. So these are our upcoming webinars. So high-level verification, system integration and analysis, place and route integration, and a deeper dive into design space exploration. And all of this, more information on our website. And I guess in conclusion, thank you very much for attending. Please contact us at any time if you have any questions or you want to learn more. We are here to help, and we would love having a conversation with you.
Absolutely. Thank you, Ellen.
Okay, thank you.